Hello, and welcome to the Robotics and Digital Media program. This is a customized program created by Discovery World's experienced teams for freshmen and engineering students at the University of Wisconsin-Milwaukee. We build robotics inspired by nature. We also learned how to conduct interviews and communicate scientific topics. Discovery World is a center for public innovation with focus on the future of the community. The purpose of the program is to encourage innovation by fusing together robotics with biomimicry, creativity, communication, and digital media production. As UWM students and tomorrow's engineers, we discover, innovate, and lead.
This is Innovation House, the robotics and digital media podcast developed by Discovery World and sponsored by the Forte program.
Forte stands for Fostering Opportunities for Tomorrow's Engineers. We are tomorrow's engineers. I'm Michael.
And I'm Nico. We're engineering students at the School of Engineering and Applied Science at the University of Wisconsin-Milwaukee.
Today, we're going to explore biomimicry and robotics.
We also have a fascinating interview with Dr. Ben Schultz, a materials engineer at UWM.
We talked about his work and his love of engineering.
But first, here's a question. Why do we love engineering?
I'm Max DeYoung, and I'm studying civil engineering at UWM. As a future engineer, I would like to be recognized for bettering humanity.
As a future engineer, I would like to design incredible and innovative new video games.
My passion is architectural and structural engineering.
My future is in mechanical engineering.
As a future engineer, I would love to create something innovative.
Engineering is all about coming up with the next big idea.
Engineers need to find creative and novel solutions to solve abstract and sometimes crazy problems.
Any innovation has to be a new idea that changes the world.
I think a great innovation is the touchscreen. They're a part of so many objects that we use.
To me, the computer is the door to everything in the world today.
A great example of engineering is Annie Frank Lloyd Wright home here in Wisconsin. He took the features of the landscape that ordinarily would be a problem and integrated them into the design.
I would like to design my own house one day, so I can be as creative and innovative as I want to be.
My parents inspired me to become an engineer. I tried it. I love it.
My high school teacher got me interested in water and the environment.
My father's a computer engineer. My uncle's a civil engineer. They showed me that being an engineer is the best thing ever.
Dean Kamen inspired me to become an engineer. He showed me that you could engineer an idea and turn it into something that inspires others.
I would invent something useful that makes everyday life better for everyone. I don't know what that is yet.
As a future engineer, I would love to create a self-sustaining energy source.
As a future aerospace engineer, I would like to make the universe a slightly smaller place.
That's why I love engineering.
And that's why I love engineering.
I'm Nina, and that's why I love engineering.
As engineering students, we love robots.
Lots of robots are designed to mimic the movement and behavior of animals. Fish, insects, people, things like that.
This kind of design and engineering is called biomimicry. It's a way of exploring the natural world and applying what you learn to solve engineering challenges in the built world.
The team here at Discovery World challenged us to design and build a robot designed by plants.
So we chose our plants, we did some research, we watched our plants in action.
We even dissected a flower and looked at it under a microscope in order to learn how plants work.
The more that we explored the plant world, the more we began to see that plants are a great inspiration for robotics.
The bean plant is a remarkable plant in nature. Hello, my name is Max, and this is Mike. We're future engineers studying at UWM.
Our robot was inspired by the bean plant, which is found everywhere except Antarctica. What makes the bean plant remarkable is that it moves its leaves towards the sun to maximize solar intake.
We designed our robot to follow a light source, mimicking what the bean plant does in nature.
This is the brick, the brain of the robot. It runs the program and the robot. These are the light sensors, which mimic the leaves of the bean plant by tracking light. These are the motors, which move in response to information from the light sensors.
And now it's time for the demonstration. I'm going to move the light, and a robot will follow it.
One challenge we faced was programming. Getting the robot to respond to light was tougher than we imagined. We solved the problem by trying different programming and adjusting the light sensors to different light levels.
We had a blast working together because we both love observing plants and figuring out how we might translate them into engineering projects of the future.
Hello, we're Spencer and Patrick.
We are future engineers studying at UWM. So, what makes the tulip fascinating?
The tulip is fascinating because it can elongate its stem and turn towards a light source without actually going through cell division.
So, our robot was inspired by the tulip plant.
We designed our robot to elongate and turn towards a light source, which is exactly what the tulip plant does in nature.
This is the brick, or the brain of the robot, which runs the program. From here to here is the body of the robot, which contains the motors and the sliders. At the top are the light sensors. These detect the light source, much like a tulip does with its leaves.
And now let's see the robot in action. I'm going to place a light source near the robot, and it will extend and turn towards the light.
One design challenge we had was combining the turning motion near the pivot with the extending motion of the sliders. We solved this problem by creating two sliders that are able to move together to extend the robot, but when only one moves, it'll turn the robot.
We had a great time building and programming our robot. It was awesome to look at nature and biomimicry. Taking an idea and creating something real is what engineering is all about.
As future engineers, we're also interested in biomimicry. Hello, my name is Matt, and this is Ernesto.
As we study engineering at UWM, we also look to nature and biomimicry to teach us about the world.
Our robot was inspired by the Venus flytrap, which is found on the east coast of the United States.
What makes the Venus flytrap remarkable is that it's a carnivorous plant. It eats bugs, but only when it can't get enough nutrients from the soil and light. It doesn't get hungry like we do. It simply gets nutrients from bugs rather than from the soil.
Another interesting thing about the Venus flytrap is that it will only capture prey when two of its trigger hairs are touched within 20 seconds of each other. We designed a robot to mimic that.
This is a brick. That's the brain of the robot. These are the gears. These are the sensors that activate the plant. And this is the motor that turns the leafy jaws of the robot.
And now it's time for the demonstration. I'm going to turn down the lights because the touch sensors will only work when there is not enough sunlight. And when the sensors are touched within 20 seconds of each other, the jaws will close in on its prey. And that was our demo.
One problem we had working through this was that the gears didn't mesh properly, and the jaws of the mechanism wouldn't close.
We solved this by experimenting with different sized gears until we found a combination that worked together. And we also had to stabilize the motor. We had a great time working together to build a robot that mimics the Venus flytrap.
Our robot was inspired by the Sensetive Plant, which is found nearly everywhere in the world. Hello, my name is Genevieve Stolenwerk.
And I'm Nina Furcano. We are studying civil engineering at UWM. The sensitive plant is considered an invasive species in many places. It is a popular plant used in science classrooms. What makes the sensitive plant so remarkable is that it responds to touch. When touched, the leaves fold rapidly. This reflex helps the plant protect itself from predators.
This is the brain of the robot, which runs the program. These are the arms, which mimic the leaves. And these are the motors that power the gears that wrap the string and fold the leaves in a cascading motion that activates the folding motion.
And now it's time for our demonstration. One challenge that we had was getting the leaves of our robot to fold with a cascading motion. We tried all kinds of gear combinations, but we finally settled on a worm gear and string because string had the right amount of slack that we needed.
This was a really exciting challenge because as civil engineering students, we got to explore mechanical engineering, biomimicry, and do a little programming. Combining different areas of study together helps transform us into future engineers.
What kind of plant is aquatic and has traps? The Waterwheel Plant does. Hi, my name is Nico.
And I'm Mitch. We're engineering students at UWM.
Our robot was inspired by the Waterwheel Plant.
The Waterwheel Plant is found from Asia all the way to Australia. It lives in ponds, rivers, deltas, and lakes, typically near the shore. The Waterwheel Plant is critically endangered because of the water pollution and loss of habitat.
The plant is rootless and floats just below the surface. It's also carnivorous. It has the same trap mechanism as the Venus flytrap, but it's much smaller and works underwater. The trap responds only to gentle pressure. This is the brain of our robot. Here is the motor. These are the two sensors. Here is the trap mechanism. This blue plate represents the trigger hairs of the plant. It is important to note that the plant will only respond to light pressure. Our demonstration is a simulation to what would happen.
One of the challenges we had was figuring out how to make the LEGO sensors only respond to soft pressure.
We solved that problem by designing this mechanism that slips and won't engage the sensor when it is pressed too hard.
You might be wondering what the tire is for. It's just a way for the robot to consistently trigger the touch sensor and doesn't represent any part of the actual Waterwheel Plant. If we had to do this over, we would try to design something a little more elegant than a tire.
This was an amazing experience because we were able to fuse together biomimicry with design, and we built a robot inspired by a plant.
As emerging engineers, we look for motivating and amazing experiences that lead us to the next opportunity. Our recent opportunity led us to explore new realms we hadn't yet tapped into.
Our guest today explores the fascinating world of metals, composites, and metallic foam.
He's a materials engineer in UWM's Department of Materials.
He specializes in lightweight aluminum and magnesium-based composites.
Dr. Ben Schultz, welcome to the program.
Thanks for having me.
What is materials engineering?
Well, materials engineering is a field in which we study the properties of matter. Materials engineers design materials and the processes to make them, and these materials can be anything from, a component that you might find in your everyday life, in your home or in your car, or it could be something that would be used in space to explore new worlds. So it's a very interesting field. I'm very excited to talk about it today.
What does your lab look like at UWM?
Well, our lab is a foundry lab. We have equipment that's meant for melting and casting of metals, mostly aluminum and magnesium, also some copper and lead and other lower melting point metals. We focus on these processes because this is the foundry industry is very big in Wisconsin and the Midwest. It's a major industry that hires our graduates. And we want to make these materials that we're developing something that can be manufactured by companies in Wisconsin.
What are you working on right now?
I'll show you one example of a metal matrix composite. This is a liner for a cylinder that could be used in a compressor. This has graphite particles in it. It's the same graphite that you would shoot into your lock to free up the key. And what we did was we mixed them into a metal, and we centrifugally cast it. It's a process that's used extensively in Wisconsin. There's a company that focuses on centrifugal casting. Because the graphite is less dense than the aluminum, it concentrates on the inside when this is spinning in the liquid state, and that makes this interior very lubricating. We call this a self-lubricating liner. On the outside, it's just the pure metal. So this is lots of applications for engines and compressors and all kinds of things where you might need something that has that lubricating property without oil. So we're doing all kinds of work on these metal matrix composites, and it's very exciting work.
It's fascinating.
What is metallic foam and how is it different from a metal?
Well, metallic foam is, this is one example of one. This is an open cell foam, and they are metals that have had gas bubble through them and then solidified so that you have these structures where it's very porous, but it still has some strength to it. I mean, I can't really bend this because it has the metal like skeleton. So these are perfect materials for crushing, because as they crush, they absorb a lot of energy, and it could be used for a bumper on your car, or it could be used as protection on a building from a blast. So we're working on a specific type of metal foam where we create the voids with these hollow balloons. There are these hollow spherical particles that we've put into the metal. Because the pores are not just holes, they have some strength to them, these little balloons. When it crushes, it absorbs a lot more energy than the ones that I just picked up before. So these are really promising materials, and they offer a potential use of a waste product. This is fly ash. This is a byproduct of coal power plants. It's sometimes put in landfills because it's a waste product. Sometimes it's used in things like concrete. We're using it in metals. If you look at the microstructure under a microscope of this material, they're little hollow balls, very much like these, except much finer. So you can create a syntactic foam that has even better properties than these big ones here, using this waste product. So that's very cheap, it's available, and it's a way to get this out of landfill, so it's environmentally friendly.
Is there a natural material that inspires you?
One that comes to mind is a shell of mollusks or abalone shells. They're composite materials, and they have actually nanostructured microstructure that gives it that strength and that ability to protect the very sensitive animal inside of it.
What would you say is the holy grail of materials engineering?
I would say that the holy grail of materials engineering would be a material that combines the properties that we currently don't have, like something that's super lightweight, something that is stronger than steel, something that doesn't corrode. We're trying to make, for example, aluminum that is stronger than steel, stronger than a lot of, titanium, but, it's not easy to do. It takes a lot of years of hard work.
Dr. Schultz, thank you very much for joining us.
Yeah, thank you.
Thank you very much for having me.
We'd like to thank Ben Schultz for joining us.
We'd also like to thank Discovery World and UWM's Forte program for making this all happen.
Discovery World is the center for public innovation. At Discovery World, we explored robotics, digital media production, and communication skills. We tinkered with new ideas like biomimicry and turned those new ideas into something real.
And that's what engineering is all about. Discovery World's experience team motivated us to discover, innovate, and lead.